Welcome everybody to another video of the regression analysis course. In this video, I'm going to prove that the estimators we obtain using ordinary least square method are unbiased. So far, we have been looking at the simple linear model, which is y is equals to beta naught plus beta 1x plus epsilon. Given any data set, we would have information about the dependent variable denoted by y. We would have information about the independent variable denoted by x. But the value of the parameters beta naught and beta 1 is unknown. And then we have the last remaining term, error term, which we denote by epsilon. And it accounts for the uncertainty in the model. So far, we have seen how to get an estimate of these parameters by minimizing the overall error present in the data set. And the particular method we use for that is ordinary least square estimation method. In this method, we minimize the sum of squared error to get beta naught hat and beta 1 hat. In the last video, we saw that these estimators we have obtained using ordinary least square method are linear combination of yi. In particular, if we see for beta 1 hat, we know that beta 1 hat is a linear combination of yi written as summation I going from 1 to n ki yi, where ki is equals to xi minus x bar divided by sxx. Before we explore the second property that the estimates of betas are unbiased, we will learn more about these KIs. So if we look at the first property of this KI, we have that if we have n observations in the data set, then the sum from 1 to n of this KI would be equals to 0. Let's prove this property. Let's consider summation I going from 1 to n KI. Plugging in the value of ki in this, we get summation ki is equals to summation xi minus x bar divided by sxx. In the last video, we discussed that this sxx we have in the denominator is a fixed quantity. And since it is a fixed quantity, we can pull it out of the summation sign. And therefore, we can write it as 1 divided by sxx times summation I going from 1 to n xi minus x bar. To simplify it further, we can distribute the summation sign over both the terms xi and x bar and get it equals to 1 divided by sxx summation xi minus summation x bar. Now, if we look at this expression, the first term we have is summation xi. Given n values of the independent variable, the average of x would be equals to summation xi divided by n. And therefore, the first term summation xi can be written as nx bar. And if we look at the second term, which is summation I going from 1 to n x bar, here x bar is the average of n values of the independent variable. And therefore, x bar is a fixed number. If we take summation of a fixed quantity or a constant, we get n times that quantity. And therefore, we have nx bar minus nx bar, which is further equals to 0. And therefore, we have the first property of ki, that is, if we take sum of ki from 1 to n, then it is equals to 0. Let's look at the second property of this ki. The second property of this ki is that summation ki xi is equals to 1. To prove this property, let's start with summation ki xi. Again, plugging in the value of ki, which is xi minus x bar divided by sxx, we get summation ki xi is equals to summation xi minus x bar times xi divided by sxx. The next thing we do is use the same logic that sxx is a fixed quantity, and since it is a fixed quantity, we can pull it out of the summation sign. Doing this, we get the second line, that is 1 divided by sxx summation xi minus x bar times xi. In the next term, we use the distributive property of multiplication and multiply this xi first with xi and get xi square, and then multiply xi with x bar and get x bar xi. In the next step, we distribute the summation sign over both the terms, xi square and x bar xi, and get this expression as summation xi square minus summation x bar xi. Now, if we look at the first term, we cannot simplify it further, and therefore we'll write the first term summation xi square as it is. But if we look at the second term, here we have summation x bar xi. X bar is the average of n values of independent variables, and therefore we have this x bar as a fixed quantity. It is a constant, and we can pull out this constant of the summation sign, and we get minus x bar summation I going from 1 to n xi. If we look at this expression now, again, we cannot simplify the first term, so we write it as it is, summation xi square. If we look at the second term, we have x bar, we cannot simplify it further, but then we have summation xi. And this summation xi can be written as nx bar. If we multiply this x bar with nx bar, we get nx bar square. So we have simplified this summation ki xi, and we have got it equals to 1 divided by sxx times summation xi square minus nx bar square. Now look at the expression we have in the numerator. It is summation xi square minus nx bar square. And this summation xi square minus nx bar square is equals to sxx. If we replace this summation xi square minus nx bar square by sxx, we have the same term in the numerator and denominator. We cancel it out and get it equals to 1. And thus we have proved that summation ki xi is equals to 1. So in the last video, when we proved that beta 1 hat is a linear combination of yi, that is beta 1 hat can be written as summation ki yi, where ki is equals to xi minus x bar divided by sxx. Now we have further explored the properties of ki, that is summation ki is equals to 0. And if we multiply this ki with xi first and then take the summation, we get it equals to 1. The reason we proved these properties is because we are going to use them to prove the second property of betas, which is the estimates of the betas, beta naught hat and beta 1 hat, obtained using ordinary least square method are unbiased. What is the definition of unbiased? Say we have a population parameter theta, and theta hat is an estimator of theta. Then theta hat is unbiased if on average theta hat is equals to theta. That is, expectation of theta hat is equals to theta. Now we will prove that both the estimates we have obtained using OLS method, which is beta naught hat and beta 1 hat, are unbiased. So let's start by proving that beta 1 hat is unbiased. We need to prove that expectation beta 1 hat is equals to beta 1. So let's consider expectation of beta 1 hat. We have proved in the first property that beta 1 hat is a linear combination of yi, and therefore we can write this beta 1 hat is equals to summation I going from 1 to n ki yi, and we have expectation beta 1 hat is equals to expectation summation I going from 1 to n ki yi. In the next step, we use linearity property of expectation, and therefore we can pull out the summation sign of the expectation, and we get summation I going from 1 to n expectation ki yi. In the next step, we use the fact that ki we have over here is dependent on the value of x. We are treating x as a fixed quantity. Therefore, this ki for each I is a constant. And we can again use the linearity property of expectation and pull out this ki of the expectation sign. And therefore, we get summation I going from 1 to n ki expectation yi. In the next step, we write expectation of yi is equals to beta naught plus beta 1 xi because we have simple linear regression model where we can express the mean of the dependent variable as a function of independent variable. In the next step, we first multiply ki with beta naught and beta 1 xi and then distribute the summation sign over both the terms. And when we do that, we get summation I going from 1 to n ki beta naught plus summation I going from 1 to n ki beta 1 xi. Let's try to simplify both the terms separately now. In the first term, we have summation ki beta naught. We know that beta naught is unknown but a fixed quantity. And since it is a fixed quantity, we can pull out this beta naught of the summation sign and we will get beta naught summation ki. And for the second term, we again use the fact that beta 1 is a fixed quantity and therefore we can pull it out of the summation sign. And the second term can be simplified as beta 1 summation ki xi. And we have just now proved two properties of ki. The first one was that summation ki is equals to 0. Therefore, for the first term, we write beta naught as it is, and then we prove that summation ki is equals to 0. And for the second term, we write beta 1 as it is, and we have just now proved that summation ki xi is equals to 1. And when we simplify it further, we get beta naught times 0 is 0, beta 1 times 1 is beta 1, and we have proved that expectation of beta 1 hat is equals to beta 1, which means that beta 1 hat is unbiased. So now we will prove that another estimate we have for the intercept, which is beta naught hat, is unbiased. But before we prove beta naught hat is unbiased, let's look at something interesting. We are dealing with simple linear regression model where for each I from 1 to n, we have yi is equals to beta naught plus beta 1 xi plus epsilon I. Let's look at the quantity expectation of y bar. The reason we are trying to find expectation of y bar is because we are going to use it to prove that beta naught hat is unbiased. So what is expectation of y bar? Given n observations, we would have n different values of the dependent variable. And y bar is the weighted average. So y bar is equals to summation I going from 1 to n yi divided by n. Now we use the linearity property of expectation, and when we use it, we can pull out the constant of the summation sign, we can pull out 1 divided by n, and we can also pull out summation I going from 1 to n because expectation is linear. And therefore, we get the second step that expectation y bar is equals to 1 divided by n summation I going from 1 to n expectation yi. Now, we use simple linear regression model and can write this expectation yi is equals to beta naught plus beta 1 xi. We have this as a consequence of the assumption on error term that expectation of epsilon I is equals to 0. And now we have that 1 divided by n summation I going from 1 to 1 expectation yi is equals to 1 divided by n summation I going from 1 to n beta naught plus beta 1 xi. In the next step, we distribute summation sign over both the terms. When we distribute summation sign over both the terms, we get it equals to 1 divided by n summation beta naught plus summation beta 1 xi. Now, we know that beta naught is a fixed quantity. Therefore, summation beta naught, the first term would be n beta naught. And for the second term, we know that beta 1 is a fixed quantity. We pull it out of the summation sign, and summation xi is nx bar. Therefore, this fourth line, which is 1 divided by n, summation beta naught plus summation beta 1 xi, can be simplified further to 1 divided by n. The first term is simplified to n beta naught, and the second term is simplified to beta 1 times nx bar. In the next step, we cancel out n because we have n in both the terms in the numerator and we have n in the denominator as well. And therefore, we have that expectation y bar is equals to beta naught plus beta 1 x bar. Remember, we have done this because we are going to use it to prove that an estimate of beta naught obtained using OLS method is unbiased. So let's prove it. To prove beta naught hat is unbiased, we basically need to prove that expectation beta naught hat is equals to beta naught. So we start by considering expectation of beta naught hat. We have already estimated beta naught hat, which is equals to y bar minus beta 1 hat x bar. In the next step, we use the fact that expectation is linear and get it equals to expectation of y bar minus expectation of beta 1 hat x bar. If we look at this expression now, the first term is expectation of y bar, and we just proved that expectation y bar is equals to beta naught plus beta 1 x bar. And in the second term, we have expectation beta 1 hat x bar. X bar is the average of n values of the independent variable. It is a fixed quantity. It is a constant. And therefore, we can pull it out of the expectation sign and we get the second term is equals to x bar expectation beta 1 hat. Now, if we look at the first term beta naught and the second term beta 1 x bar, we cannot simplify it further. And therefore, we write the first two terms as beta naught plus beta 1 x bar. We write the first two terms as it is. If we look at the third term, we have x bar times expectation beta 1 hat. We have just proved that beta 1 hat is unbiased. That is, expectation beta 1 hat is equals to beta 1. And therefore, the third term can be simplified to x bar times beta 1. And now we have beta 1 x bar minus beta 1 x bar, which cancels out and we get beta naught. And we have that expectation of beta naught hat is equals to beta naught, which means that beta naught hat is unbiased. So in this video, we learned that beta 1 hat and beta naught hat, an estimate of beta 1 and beta naught obtained using ordinary least square estimation method are unbiased. That is, expectation of beta 1 hat is equals to beta 1 and expectation of beta naught hat is equals to beta naught.